We have been looking at functions that are continuous functions and some that have some discontinuities. So remember that we have some functions with some types of discontinuities, and we're going to look at some of those in this video and some of their characteristics. So remember that many rational functions, not all of them, but many of them, and the following trig functions, tangent, cotangent, secant, cosecant, arcsecant, and arccosine, are all continuous at points where they're defined, but are not continuous functions because their domains are not a single interval of the real numbers. So they have places where they are undefined, which of course give discontinuities. Now let's look at what kind of things we've seen. We have seen places where the limit as x approaches c of f of x exist, but f of x is f is undefined at x equals c, and this gives us a hole in the graph with no point of the graph on the vertical line x equals c. Okay. We also have things where the limit as x goes to c of x and f of c are both defined, but the limit as x goes to c of x is not the same as the limit as f of c. That's also a hole in the graph with an isolated point on the graph of the vertical line x equals c. So the isolated point of the graph, and that point of course is c comma f of c, is actually on the graph, but it's on the vertical line x equals c, but not. But there's also a hole. Let's say this is L. Okay, is the limit. Then there's a hole in the graph at c comma L with an isolated point on the graph c comma f of c. So those are not the same. And of course we've seen places where it's continuous. But we've also seen places where the limit is undefined at x equals c. This is some kind of non-removable discontinuity. It's not a hole, it's something else. So one way we've seen this is the limit from the left as x approaches c from the left of f of x, and the limit as x approaches c from the right of f of x are both defined, but they're not equal to each other. Then the graph has what we would call a jump discontinuity. And then we also have vertical asymptotes, and that's when the limit as x approaches c from the left of f of x, or the limit as x approaches c from the right is either positive or negative infinity. Then the graph has a vertical asymptote at x equals that c value. So we've seen some of those. So first of all, we've had functions that had a finite number of removable discontinuities. Basically, it's a continuous function with a few holes punched in it, so that it doesn't have, so it's no longer continuous. It has discontinuities here. Now, one easy way to take a function to get a hole at a point, say a point AL, is to take a function which is continuous at x equals a with g of a equals L, and then define the new function f of x is the g of x times x minus a over x minus a. So in other words, if you take a function and you multiply by x minus a over x minus a, that's going to punch a hole in that function where x equals a, provided it isn't already undefined there, or didn't already have a discontinuity there. So if g of x was continuous at x equals a, and you multiply it by x minus a over x minus a, then the limit will be the same thing as the limit of g. The limit as x approaches a will be g of a, and so a comma g of a will be a hole in the graph, but f is undefined at x equals a. So, and you can do this repeatedly and punch as many holes in a graph as you want, provided there's not already a discontinuity at the point where we want the hole. So, for example, we could take a nice solid line, 3x plus 2, and we could punch holes at x equals negative 1, 2, and 5 by taking the 3x minus plus 2 and multiplying by x plus 1 over x plus 1, x minus 2 over x minus 2, and x minus 5 over x minus 5. This will look just like a line with 3 holes in it. So we can easily get a finite number of discontinuities that way. So we also have rational functions. So in rational functions, the holes can kind of be thought of as coming from this sort of a process. So there would be a finite number of holes in a rational function, and it will have a finite number of vertical asymptotes. Now we've had rational functions that are actually continuous functions. Certainly polynomials are rational functions, and they're always continuous. We've had other rational functions where the denominator is never 0 for any real number inputs, and so that turns out to be a continuous function. But we've had other rational functions where the denominator is 0, and each one of those x values will give you either a hole or a vertical asymptote. We had some with holes, we had some with vertical asymptotes, we had some with both. But there's always a finite number of them because there's only a finite number of places the denominator can be 0. Now we also have infinitely many periodic asymptotes occurring for the basic trig functions tangent, cotangent, secant, and cosecant. And if you look back a couple of videos or to my trigonometry videos, you can see lots of more details about these functions. But you notice that they have infinitely many discontinuities, which are always vertical asymptotes, and they actually occur periodically. Now, in fact, here are the graphs there. There's tangent, cotangent, secant, cosecant. You can see those, and you can see the vertical asymptotes. Now, jump discontinuities typically happen when we have piecewise defined functions or we have some kind of rounding involved. For one example of a piecewise defined function that has a jump discontinuity is the signum function or sine function, S-I-G-N, not S-I-N-E, the sine function or signum function. And it has a jump discontinuity of 0. It's actually defined for all real numbers, and it's written as SGN of x or SIGN of x. And the output is -1 when the input is negative. The output is +1 when the input is positive, and the output is 0 when the input is 0. So basically, you want to think of it as it just retains the sign only and not really the magnitude. So all of the negatives are sent to a -1 and a magnitude of 1, and all the positives are set to magnitude 1 of 1, and 0 is neither positive nor negative. It's left alone at 0. Well, if you graph that, look what you get. You get a horizontal line here at -1, so this should have an arrow to the left, has an open dot right here at 0, -1. Then when x is 0, it jumps up to this solid dot isolated point right here at 0, 0 at the origin. You have an open dot boundary point at 0, 1, and then from there it goes on the horizontal line y equals 1 to the right, arrow on the right. So the limit as x goes to infinity is 1, the limit as x goes to negative infinity is -1, the limit as x goes to 0 is undefined, and the limit from the right is 1, the limit from the left is -1, and the value is 0 when x is 0, approaching 0. And so we see we have a jump discontinuity here, so it jumps from -1 to 1, sort of by way of 0, you might say here. And so we have a jump there in it. A type of rounding function, there's several different types of functions that round different ways. Here's one example. One is the greatest integer function, or also known as the floor function, and here are several different notations for it. The greatest integer function is sometimes done with these double line brackets. You also see it written as int of x. You also see it called the floor function. It's just called floor of x. Or you'll see a bracket like this with the little square legs on the bottom but none on the top. That's called the floor function. And what it is, it's the maximum of all a's such that a is less than x and a is an integer. So it's the greatest integer that's less than or equal to the number we're wanting. So what it does is it's the round down function. So it takes numbers, say a 1.3 would round it down to 1. It takes 1.7 rounds it down to 1. Of course, the integers it leaves alone, 1, 2, 3. So it has solid dots on this line y equals x at integer coordinates, what we call lattice points, -2, -2. -1, -1, 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. So that's going up just a straight line, but in between, it's not on that straight line, it's on horizontal line segments. So this would be an example of what we call a step function, because this looks kind of like stair steps. And notice it has a jump discontinuity at each integer. So all the numbers between 0 and 1 have an output of 0, but 1 has an output of 1, so there's a jump discontinuity there. So each one of these line segments has a closed dot on the left, and it should have an open dot on the right, like that. There's some variations of this, the ceiling function and the rounding function, and they have similar kinds of characteristics, but a little bit different. Now, actually, you might think of this, you think, well, everything we've looked at mostly has been continuous everywhere it's defined. You know, things like, that's certainly, you know, you got continuous functions are continuous everywhere, like polynomials and sine and cosine, for example. You got functions that are continuous everywhere they're defined, like rational functions and all the trig functions. You've got things that aren't continuous where at some points they're defined, but they're just a certain number of places. Like this one has one single jump discontinuity right here. It's defined there, but we still have a discontinuity. The greatest integer function has infinitely many discontinuities, but at least they're only at the integer values. How about a function that's not continuous anywhere? You might not think such a thing actually exists, but such functions do exist. Here's a function that's not continuous anywhere. It's a piecewise defined function where f of x is 0 if x is a rational number, and f of x is 1 if x is an irrational number. So no matter what x, say what value c we pick, x equals c, if you take the limit as x approaches that, there are always numbers within any, no matter how small you make delta, there are always numbers within delta that are 1 away. So every single point on this thing is actually an there isn't actually a point where it's a discontinuity. So it's kind of like you've got two horizontal lines, one at y equals 0 and one at y equals 1, but both lines are just completely riddled with holes. You know, the line at y equals 1 only has x values where x is irrational, so it has holes at all the, not really holes because holes are really you know, removable discontinuities, but it has empty spaces where x is rational and vice versa for the other one. So a pretty wacky function there. Not what I would call one of our elementary functions, but definitely something that's interesting. When we looked at end behavior, we had different things that could happen. We had certainly had functions which went off to infinity or negative infinity. For example, polynomial functions always go off to infinity or negative infinity as you go far to the right or left. But we did have some which had some limits, and we had some different things that could happen there. For example, rational functions, if they do have a limit as x goes to infinity, they have the same limit as x goes to negative infinity, so they will have a horizontal asymptote in that case, and they always have the same asymptote on both ends. So if it has a horizontal asymptote, a rational function will have the same asymptote on both the left and the right. Some functions have an asymptote on one end, that is, it has a limit on one as x goes to infinity or maybe negative infinity, but not on the other end. A good example of that would be exponential functions. They always have a horizontal asymptote on one end and no asymptote on the other end. But you could have different asymptotes on both ends and still have them. So that happens for some functions. Logistics functions had that, as well as an arctangent and an arccotangent had different asymptotes on both ends, but did have limits. So the limit as x goes to infinity, the limit as x goes to negative infinity, they both exist, but they're not the same value. For example, arctangent, we know the limit on the left is 0, and the limit on the right is pi over 2. No. The limit on the left is minus pi over 2. The limit on the right is pi over 2. That's correct. Okay, now as always with my notes, it's always good now to actually read a textbook you may have assigned. For example, this current semester we're using this particular book by Stewart, and it's time to read these corresponding sections, and maybe the pre-calculus stuff from chapter 1. Whatever book you might be using, it would be a good time to read that for some extra thing. At the bottom of my homepage on the YouTube videos, I have some links to some other folks' videos. Dr. J.C. Price, a colleague of mine, formerly of my university, is he's done some nice videos. He has a series of videos summarizing elementary functions, and about 3 up so far talking about limits. Those are actually quite good. Khan Academy always has a lot of good resources there. Here's some links to a video about the squeeze theorem and some things about limits and epsilon delta limits and so forth. And there's some other videos that you can look at online. But hopefully this set of videos that you've seen here will give you a nice introduction to limits. We've looked at limits informally in section 1. Part 2, we talked about limits more formally, got our hands on the epsilon and deltas and looked at the definitions and look at that and some of the properties of limits and using them. And this part 3, we end up by going back to look at some pre-calculus material and thinking about some of those basic functions that we learned in pre-calculus courses like algebra, trigonometry, a little bit even probability statistics. And we looked at those functions and said, okay, which ones of those are continuous? Which ones are continuous where they're defined? What kind of discontinuities would we have? And so hopefully this gives you a nice introduction to an overview and some detail on these particular topics.